Good afternoon, everybody. Hope you're doing well today. Please go to the chat and tell me where's the best place you've ever been on Earth. Maybe you visited there, maybe you live there now. What is that place? Try to not pay attention to my notifications. What that was. Okay, so any questions, feedback while we're waiting for people to do that? Anybody? Okay.
I have one.
Yeah, what's up?
In lab on Monday, Dr. Chandra was mentioning a lot about histograms and I think something called like the Gaussian slope. Are we going to get to that within like the next 2 weeks?
Yes, today we are starting histograms, and we should be finishing up the Gaussian stuff on Thursday. It might spill over a little bit to Tuesday next week.
All right, thank you.
Sure. Other questions? Anyone? Alrighty. We're going to head immediately into breakout rooms today. And I want you to, I'm putting just to remind you of your breakout rooms again, just in case I'm putting that into the chat. And I would like for you to please review your answers. Review your answers for the problem we were working on last time, mean and standard deviation, problem number 3 from our As You Learn page. So I copied those problems and put them down here in week 6. So it's number 3 at this link, mean and standard deviation in class problems. So please go to your breakout rooms in just a second and discuss your results for that problem, or B. Well, A and B. We already talked about A, I think. So mostly talk about B. All right, rooms should be open. Go have fun. All right, folks, did we get similar results or any results for part B of number 3 of our mean and standard deviation problem? Allison, you're nodding. What'd you get?
For my standard deviation, I got 3.31 or 3.32.
For your standard deviation, in part B, what are we talking about? Okay, let's review the problem, make sure we all know what's going on. Maybe I don't. We're talking about these problems here. Y'all let me know if you have issues with Word files. I won't post those anymore if that's a problem. Okay, so we're doing number 3. Oh my gosh. A student walks into a room and figures out the resistance of these values. This is what you were doing, right, Allison? No. Okay. Did anybody do this problem? Part B from last time. Just now in their breakout rooms. Okay.
We were working on it.
Yeah, we were working on it. We just didn't finish.
Didn't finish. Okay, sorry. Cool.
It's okay.
All right, well, let me show you what I got, and hopefully you were on the same track as what I did here. So we're gonna back up and review. We had this person and they have these measurements of voltage and amplitude going through a resistor. So the voltage and amplitude correspond for each column here. And the student was supposed to calculate the corresponding resistance value with this equation and put that into the chart. So we did this last time, just reviewing. Once we put those values into the chart, we found the best estimate for the resistance. So we found the mean 2.43 ohms of those measured values, and the standard deviation was 0.0294 ohms. Then we found the standard deviation of the mean by taking the standard deviation and dividing by the square root of the number of points, dividing by the square root of 4. So then we got 0.0147 ohms, keeping all the sig figs for calculation purposes right now. Okay, if we're going to write that as an uncertainty, the uncertainty in the average is the standard deviation of the mean, and we round that to 0.02 ohms then, if we're going to write it as an uncertainty. But we will keep the standard deviation of the mean in terms of more than one sig fig for calculation purposes, if we use that in the future. Okay, in part B, we're told the resistor is rated at 2.5 ohms. That is the true value of this resistor. And so that is not explained by the random uncertainty. That means if we plot on our resistance axis here, we can show a line that indicates the true value, 2.5 ohms, and a line that indicates our average mean value, 2.43 ohms here, that's the dot. And then there's a range around that 2.43 of 0.02 plus or minus 2.43 plus or minus 0.02 shown here. So that's the uncertainty range based on that standard deviation of the mean that was rounded up to 1 sig fig, which is our uncertainty in our mean. And we can see that this range, I'm sorry, it's kind of small, sorry, I'll zoom in, but the range does not encompass the known correct value for R. So then the lab tech tells us, oh, well, there's a 2% systematic uncertainty that you should expect from the ammeter and the voltmeter. Thanks for telling us that now, lab tech. So then we're supposed to use error propagation to now also take into account this 2% error that we know is happening in our voltmeter and our ammeter, measuring our current and measuring our voltage across the resistor. Current through the resistor, voltage across the resistor. We are told to use error propagation to find the systematic uncertainty that would relate to this 2%, like in terms of ohms, and then combine that with our random uncertainty, which we already found. That was this 0.02 ohms, our standard deviation of the mean, our uncertainty in the mean. We're going to combine those in quadrature and get a total uncertainty. Okay, so we're told that the uncertainty, the systematic uncertainty, is 2% of the reading for the voltmeter and for the ammeter. Somehow it's the same for the two instruments. So we measured 2.43 ohms as our reading, as our average reading. And so our systematic error uncertainty is going to be 0.02 times 2.43 ohms, which is 0.0486 ohms. Keeping sig figs again here because it's a calculation, so showing all of them there. But then I'm rounding to 1 sig fig here, showing that the uncertainty due to that systematic error in that device is 0.05 ohms. So now I know my systematic uncertainty, 0.05 ohms, and I know my random uncertainty, 0.02 ohms. Both of those contribute to the final wrongness of my measurement. So I need to take them both into account, into a total uncertainty that is going to predict that wrongness better. So I take 0.05, square it, 0.05 ohms and square it. I take 0.02 ohms and square it and add them up. I'm showing all the steps here because if you make a mistake, you can like look at my step and maybe find your mistake easier. So we end up with 0.05 ohms as our total uncertainty now, based on that calculation. Okay, now they ask us, how does that final value compare to the given value, the new final uncertainty range? We have a new range now. We have a new range around our point here to consider. Is it going to encompass that star or not? Okay, so I zoomed in, rewriting the values. The old value was 2.43 plus or minus 0.02 ohms. That was just with the random uncertainty. Now our new value is 2.43 ohms plus or minus 0.05 ohms. That's our total uncertainty that also includes the systematic uncertainty. And we have this new chart. Our point is still centered on 2.43 ohms, but our range is bigger now. It goes up to 2.48 ohms and goes down to 2.3678 ohms. So that range is bigger, but it still does not encompass the 2.5 ohm true value. The star is not inside the range. So the new total still does not account for all the problems. There's still something going on we haven't explained yet. If the star was inside the range, then we'd be like, okay, it's all explained. We got that systematic uncertainty from the devices and whatever other random uncertainties are happening that we accounted for. And then that would be great. But that's not happening. We still have to figure out, we still have to keep looking for what might be causing our value to be wrong, our measured value to be wrong. There's something else we're not seeing here. Questions about that? Cool. So that was the mean and standard deviation problem number 3. We also looked at this problem last time, the counting problem from Taylor, problem 4.6. So we're going to go back and take a look at that from last time really quick. Here. So counting experiments happen when you count things like radioactive emissions or products on a conveyor belt. And for the uncertainty of a counting experiment, we were told that we could use the square root of the average counts. You take how many counts there are per session of counting, and then find the mean of those counts. And then the square root of that mean is going to be our uncertainty, which should also be the same as the standard deviation. But finding the standard deviation takes a lot of steps. And taking the square root of an average does not take a lot of steps. So in 4.6, we illustrate this this nice way of kind of taking a shortcut to find the uncertainty for a counting experiment. So here was the problem. I'm going to delete this. And we worked on this last time in breakout rooms. I'm not sure anybody actually had time to calculate that standard deviation. It took me quite a while to not make a mistake because there's lots of steps. So I'm just going to go through it with you. And we're going to find the mean and the standard deviation of this counting experiment set of numbers. And then we're going to show that that is almost the same as the square root of the mean. The standard deviation is the same almost as the square root of the mean. Okay, questions before I continue? Here we go. So this is on the As You Learn page already. If you want to look there, you can look separately. I just wrote it straight onto the piece of paper. So first we're supposed to find the mean, and there's 20 different points. There's a person using a Geiger counter, just to remind you, and they measure how many counts in several 2-second intervals. So here's one 2-second interval, here's another 2-second interval, here's another 2-second interval. And they do this 20 times. And here's all their different counts per 2-second interval. So in part A, we're supposed to find the mean and standard deviation. This was really fun. This is what Sean was asking not to do by hand last time. So to find the mean, we add up all of those counts, add them all up, and we divide by 20, the number of measurements, and we get 10.7. We all agreed on that last time. Then we find the standard deviation. That's where we take 1 over, sorry, there's supposed to be a square root over that. We take 1 over n minus 1 times the each value minus the mean quantity squared. And we add all those up and take the square root of all that and multiply those. So here I've put in each value, 10 minus the mean, 13 minus the mean, 8 minus the mean. I'm just going through all the points. And I just numbered them down here to help myself keep track. All right, so the next page shows those differences, and then we need to square each of those differences. I'm just writing them all positive there. And then there they are squared. And then I add them all up and get 220.4. Took the square root of that, multiplied by 1 over 19, square root of 1 over 19, and I got 3.4. Did anybody else do that? And or did you see a mistake in what I did? Did anybody else get this result? If you worked on that. This is a homework problem you will have to show. So you will have to eventually show this, compare it to mine. Don't assume mine is correct. There might be a mistake, but it's pretty close, I think. I'm pretty sure.
I got the same answer as you, Dr. Hester.
Cool. Thank you, Gabe. It must be
I
right.
also got 3.37,
Okay.
which is close.
Thank you, Jess. Yes, very close. Okay. So that is what me and Jess and Gabe got for the standard deviation with this many steps. I mean, look at how many ways there are to make a mistake. A lot. Took me a lot. You see a lot of erasing here and me doing this over and over. The easier way to do that is to take the square root of the counts. If we take the square root of the counts, we get 3.27, which is very close to 3.4. And in general, it's going to be that close every time. So we're not showing it with a proof, we're showing it with an example. You're welcome to calculate the standard deviation, but you can also take the square root of the mean of the counts to spare yourself the arithmetic and the chance of making a mistake. Okay, questions, comments, feedback? Alrighty. We have a new problem on the As You Learn page. Counting experiment in class problem 223. I will display it on my screen. And you can also, look at the As You Learn page to get it if you want to look at it on your own. And we're going to go in breakout rooms and we're going to do parts A and B of this problem. There's only 5 points. There's not 20, so it's not as horrible as the last one. So go back to your breakout rooms and I'll see you in a few minutes. Are they open? Alrighty, welcome back, folks. Anybody want to tell me what you got for your mean value?
We got 15.4.
Me too. Okay. And how about for standard deviation?
3.5.
Say it again.
3.5.
Yeah, I got 3.5 as well.
Okay, cool. Hopefully we all got that. That's what I got as well. I'm going to share my screen. I can show you how I did it. So to get the mean, I added everything up, divided by 5. I got 15.4 counts. And this time I actually calculated it without the 0.4. I included that extra digit when I did this calculation before. And I didn't include it here. Alex, did you include that 0.4 in your calculations? And whoever else was saying they got that?
Yeah, I did.
Abdel? Okay. Well, I didn't, and we got the same thing. So it's probably better to include that, but if you don't have time, sometimes it's okay for like a quick answer. So then we are supposed to find the square root of this expected, of the mean, excuse me, to compare to that standard deviation. What did y'all get for the square root?
3.9.
Okay, I did too. So the square root of the mean number of counts, so 15.4 or 15, the square root of that is going to be about 3.9, which is not exactly equal to the standard deviation that we found of the counts, 3.54. But they're pretty close, again. And this was, again, way less steps. Taking the square root was a whole lot less steps than taking, finding that standard deviation. So they don't perfectly match, and that's what part C is all about in this problem. So in part C, you're assessing how much they don't match, and there's a way to quantify that, to figure out how wrong your estimate of your standard deviation is when you're just taking that square root of the mean counts. So I want you to do part C on your own in order to understand how to quantify that wrongness of your estimate. And I will post my solution so you can compare it next time. Questions about this counting experiment problem? Anyone? Okay. Then we will move on to histograms. I think that was next. Check my agenda real quick. Yes. What's a histogram? Anybody? Anybody know?
It's where you got take all your data and then you put it into like bins where it's like ranges of values, and then you count how many of your data points are in each bin, and then you make little bars for each bin.
People who were in my classes, you've seen histograms. Every time we had an exam, we would look at the histogram afterwards. Yes, thank you, Sean. That was correct. So here's an example of a histogram from a test. This was exam 4 in Physics 1151. No, Physics 1150 in fall 2018. I think some of y'all might have been in that class. Maybe not. Maybe you were. Anyway, so here was exam 4. This is the histogram that I showed everybody after the exam. People did pretty well, mostly in the 80s, but we see that there was also some 70s and 90s, and then a few like pretty bad grades, and then a couple really good grades. So a histogram, like Sean was saying, is something that has these bins. So the bins is the number of categories. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 categories here. And when we're counting, we're going to be counting per bin, per category. Previous to now, we've been talking about counting experiments where we count the same thing over and over. We count radioactive emissions in 2 seconds. So we count radioactive emissions in 2 seconds, and then we count radioactive emissions in 2 seconds, and we keep doing that, and it's the same thing over and over. But what if we're counting different things? What if we're counting number of people who got in the 90 to 99 range? And we're counting the number of people who got to the 80 to 89 range, and so on and so forth. Now our counting experiment has now different categories that we are counting. And that's when a histogram becomes useful. We don't have different categories, it's kind of silly, but we do have different categories. It's very useful to view that data. So that is what a histogram is. So it answers the question, how many of each category are there? It shows us the number of things per category, like this call center hold time graph, where we have the number of customers willing to wait and then how long they wait. Human behavior is typically Gaussian like this. We'll see what that means exactly later, Gaussian, like Brendan was asking about. But yeah, most people are willing to wait. A lot of people get off right away. Most people are willing to wait for, about 5 minutes, and then you don't have a lot of people willing, not as many willing to wait after that. So each category has a certain number of people who are willing to wait a certain amount of time, and that's what's shown here. All right, now let's talk about bar histograms, and I'm gonna try to make this bigger so you can see it better. There's different kinds of histograms. Here we're talking about a bar histogram. In a bar histogram, we follow this framework listed here on the left-hand side of the slide. K is the number of bins. F sub k is the fraction of things in that bin. Little n sub k is the number of things in that bin. And big N is the total number of things counted. So the fraction of the results in bin K is going to be equal to the number of things in bin K divided by the total number. And F sub k is the height of the bar shown in the bar histogram on the y-axis. So it's a fraction. The y-axis is a fraction or a percent. And if you add up all of the fractions, all of the percents, you should add up to 100%. Like if you take all your groups and add up all your things, you should get your total number of results back. So if you sum up all your F sub k's from the F sub k from each bin and add them all up, you're taking all your fractions and adding them up, so you should get 1 if you're thinking in terms of fractions, or 100% if you're thinking in terms of percents. So this is called the normalization condition. It just means we're using percents, like we have a percentage y-axis or a fractional y-axis. Unitless. Just numbers, just like percents. Okay, so here's an example. Here we have the number of hours slept by animals at the zoo in a 24-hour period. We have chosen to have 8 bins here. We don't know how the data was collected. I'm going to assume it was collected very diligently and that the final data was grouped into these 8 bins. So if the animal slept between 0 and 3 hours, that counted for this bin. So that was 12%. And then from 3 to 6 hours was 8%. And from 6 to 9 hours was 28%. And so on and so forth. So if we add up all these percents, we should get 100% back. And we do. We add up 12 plus 8 plus 28 plus 20 plus 12 plus 8 plus 5 plus 7, and we get 100% back. So this is what we call a normalized bar histogram. Questions about the bar histogram? Okay. I was not showing normalized histograms when I was showing you histograms in class. If we add all these up, it does not add up to 100%. This is just a number of people here instead of a percent here or a fraction. So this was not normalized. But if we do have, if we do have this framework, then we have a normalized histogram. Okay. Here's another sort of just further showing what was happening in that previous slide. And a new idea to realize. If we do have a normalized bar histogram, we can find the mean value of the counted things pretty easily. So if we take the, go back and see what that is. If we take the fraction per bin and multiply it by the number of items and add those up per bin, then we're going to get the average value. And so here we did that. We took 0.12 instead of percent. We converted that to a fraction. I'm sorry, to a decimal. 0.12 times 1.5 hours. And 0.08 from the next bin times 4.5 hours, and so on and so forth. If we do all the math here, we're going to get 10.2 hours as our average value. And that's what I put into the plot here in the that dashed line there, which makes total sense. It looks like it would be, by eyeballing the graph, it looks like what you would expect the average value to be. Okay. Questions about bar histograms? Okay. Now there's this other kind of histogram called bin histograms, and they're different. In a bar histogram, we only care about the height of the bar. Like in this example, the height of the bar was the only thing that really had meaning. The width is arbitrary. It's just like wide enough so you can see it. But a bin histogram now is going to have a width that matters. The height and the width are both important for a bin histogram. For a bar histogram, height is the only thing that is important. So for a bin histogram, we're now going to have this fraction, this f sub k, remember, was the fraction of results in bin k. That's going to be equal to the height times the width of that bar, of that block, I should say. If all the bins are the same width, it's not really that different from a bar histogram. A bin histogram is really pretty similar to a bar histogram, pretty much the same, if all the bins are the same width. But we can change the bin width sometimes for a reason, and then things look different. And I'm going to have to stop here. Here's an example of a picture where a bin width is not the same everywhere. It looks weird, but that's what it is. We're going to elaborate on bin histograms and then get to how does this actually have anything to do with distribution functions and Gaussian functions and continuous things. We'll talk about that next time. So have a good week. I'll see you Tuesday.